1.1.
Obviously, navigation is the primary application of most GPS devices.
Sure.
Then you've got associated applications, uses that are related to navigating, such as tracking systems you can use for monitoring delivery vehicles and finding stolen cars, that kind of thing.
Mm-hmm.
And then there are more creative features. A good example would be on a boat GPS. You get drift alarms. So, if the anchor starts to drag and the boat starts moving, there's a setting on the GPS that allows it to detect the movement, and an alarm sounds to warn you, and prevents the boat from drifting unnoticed.
I see.
Or, another example on boat systems is man overboard buttons. So, if you're sailing along and someone falls into the sea, you hit a button which logs the position and ensures that you don't lose track of where you were, which then enables you to turn round and come back to the same point and find the person.
Right.
So, these are the kinds of applications we want to develop, more specialized and more creative.
So, effectively, you're not talking about technical innovations. What you're really looking for is innovative ways of actually using the technology.
Precisely. Because in these days, from the end user's point of view, accuracy is no longer the main selling point. Most devices are accurate enough. The key is to make them more useful. So, in terms of development, that's the kind of innovations that we want to do.
1.1.
Obviously, navigation is the primary application of most GPS devices.
Sure.
Then you've got associated applications, uses that are related to navigating, such as tracking systems you can use for monitoring delivery vehicles and finding stolen cars, that kind of thing.
Mm-hmm.
And then there are more creative features. A good example would be on a boat GPS. You get drift alarms. So, if the anchor starts to drag and the boat starts moving, there's a setting on the GPS that allows it to detect the movement, and an alarm sounds to warn you, and prevents the boat from drifting unnoticed.
I see.
Or, another example on boat systems is man overboard buttons. So, if you're sailing along and someone falls into the sea, you hit a button which logs the position and ensures that you don't lose track of where you were, which then enables you to turn round and come back to the same point and find the person.
Right.
So, these are the kinds of applications we want to develop, more specialized and more creative.
So, effectively, you're not talking about technical innovations. What you're really looking for is innovative ways of actually using the technology.
Precisely. Because in these days, from the end user's point of view, accuracy is no longer the main selling point. Most devices are accurate enough. The key is to make them more useful. So, in terms of development, that's the kind of innovations that we want to do.
1.2.
The engineering challenge of connecting a satellite to Earth using a cable is obviously significant. In order to support its own weight and be securely attached at each end, the cable would require a phenomenal strength-to-weight ratio. Carbon nanotube materials might one day be up to the job, and I'll talk about those in detail later on. How could vehicles be raised into space up the cable? Well, using a self-contained energy source would be problematic due to the weight of fuel or batteries required to power the vehicle. There are two possible ways around this problem: transmitting electricity wirelessly or using solar power. The first technique is only in the early stages of research. The second would allow the vehicle to ascend only very slowly, though this wouldn't necessarily be a problem, as the car could be controlled remotely, allowing it to transport payloads as an unmanned vehicle.
1.3.
The offshore base station would be supported by a floating structure which could be attached to the seabed by anchors. Payloads could be carried from the shore to the station by ship before being lifted into orbit. The main advantage of a floating mobile station rather than a fixed base on land would be to help reduce the risk of a collision between the cable and one of the many lumps of space debris, such as redundant satellites that litter orbital space. Based on careful monitoring of debris movements, in the case of an alert, the station's anchors could be raised and the station could be moved, driven by propellers, to a new location out of harm's way.
1.4. 1.
So, as you can see from this cross-section, we've come up with a completely unique profile. It's exclusive to this company and unlike anything else on the market.
2.
One of the key advantages of this new form is that it dramatically reduces vibration, which was always a problem before. Obviously, machines like these can never be entirely free from vibration, but the new design runs extremely smoothly.
3.
Another advantage of the new profile is that it's considerably lighter due to the reduced area of the overall section. So compared with our previous range, it's highly efficient, especially in applications that require continual starting and stopping, where low inertia is important.
4.
We are still conducting long-term reliability tests, but trials so far suggest the design is exceptionally durable, primarily as a result of the low vibration levels. We expect it to be significantly more reliable than rival units that are on the market, which is obviously an important selling point.
1.5.
If you're talking to non-specialists and you start using jargon, then to your audience it's just going to sound like nonsense. That's one problem. Another relates not so much to language, but to the complexity of the technology you're talking about. Even if you use everyday language, the engineering concept itself might still be difficult to explain. And that can make the subject very heavy-going and quite dull, which is obviously not what you want. However, I think it's important not to oversimplify things. There's nothing worse than being spoken to as if you're a child. You don't want to sound patronizing.
1.6.
It's obviously best to use everyday language as far as possible, but I don't think that means avoiding jargon altogether. I find the best approach, so as not to sound patronizing, is to use a certain amount of technical language and then immediately afterwards give straightforward explanations of what it means using everyday words. When it comes to explaining tricky technical concepts, a good technique is to make comparisons between the technical point you're trying to illustrate and things from everyday life that people are familiar with, to help them paint a picture in their minds. And then, to help lighten things up and stop things from sounding dull, I think it's good to use a bit of humour as well, and maybe a few amusing anecdotes.
1.7.
As you can see, we've started work on the substructure. In other words, the part of the structure that's below ground level.
Right.
See there.
The foundations are concrete piles. Basically, a pile is a column going down into the ground. And we're using what we call bored in situ concrete. In other words, we bore or drill a hole in the ground and concrete's poured in situ, which means it's actually poured on the construction site in its final position.
Yeah.
An alternative is to use what we refer to as precast-driven piles. Precast refers to the fact that the piles are made at a factory away from the site before being delivered. They're then driven into the ground. They're hammered in with a pile driver, which, put simply, is just like a giant hammer. And they don't just drive in piles, they drive everyone mad with a constant boom, boom, boom all day long. So, thankfully for our ears, we're not using that technique. Instead, we're boring the piles. The pile auger over there is effectively just like a giant drill. As it drills into the ground, we pump a special liquid called bentonite into the hole.
Right.
Essentially, it's a kind of clay suspension, a sort of mud. And that prevents the walls of the hole from collapsing inwards.
Right.
So, when the hole's finished, it's full of bentonite. It looks just like a big, muddy puddle on the ground. Obviously, it's not a good idea to step in one, like a colleague of mine once did, and then had to drive home in his underpants for a change of clothes. So, once the hole's been bored and filled with bentonite, they lower in some steel reinforcement, and then concrete's pumped in. And because the concrete is denser than the bentonite, it displaces it. So, in simple terms, if you picture a glass full of water and imagine pouring concrete into the glass, the water would overflow and you'd end up with a glass full of concrete. So, that's piling. If anyone has any questions, by the way, just go right ahead.
2.1.
The only way to assess the environmental impact of a given material properly is to carry out an environmental audit and analyze the total impact of that material on the environment. I emphasize total impact because it's all too easy to judge materials and products on single aspects of their ecological impact. As an example, if we compare traditional and energy-saving light bulbs, it's tempting to say energy-saving ones are better because they consume less energy. In fact, that's only part of the picture. That's just the in-use phase. You also need to consider the pre-use phase. In other words, the environmental impact of mining the materials used to make the bulbs, of transporting those materials to the factory, of manufacturing them, etc. Then there's the post-use phase. How easy is it to recycle spent bulbs? And when you start to consider all of these factors, suddenly the comparison between classic bulbs and their energy-saving equivalents becomes much less clear-cut. Some of the materials used in energy-saving lights are problematic from an environmental standpoint, both in terms of acquiring them and recycling them. So the point is, it's essential to look at the whole picture. And doing that can be quite a complex task, as we'll see later on in
2.2.
Okay, so steel bodywork versus aluminium bodywork.
What about pre-use then?
Well, I think it takes a lot of energy to produce aluminium compared with steel, because aluminium's made by electrolysis.
Yeah, so steel's better, presumably.
I think so, yeah. But hang on a minute. With aluminium, it depends how much is derived from ore and how much is recovered from recycled material. As far as I know, recycling aluminium takes less energy, so I'm not really sure.
Presumably it'll be mixed, won't it? For a given batch there'll be so much new material and so much recycled material.
Probably, yeah. Okay, so that needs to be researched then.
Is car bodywork galvanised when it's made from steel?
Oh, good question. I'm not sure.
If it has to be coated with zinc, then that would take extra material and extra energy, so that's an important consideration.
True. Okay, so that's another question to note.
Then there's the energy consumed when they're transporting bulk metal to the car plant.
Presumably aluminium takes less energy to transport, being lighter.
I'd say so, yeah.
Okay, what about manufacturing?
Well, aluminium would be lighter to handle, wouldn't it? It probably takes less energy to cut as well.
Yeah. Not sure whether it takes less energy to weld compared with steel.
Good question. Another thing to check out.
What about in-use then? I assume aluminium's better because it's lighter, so you consume less fuel.
Yeah, and it should last longer as well.
Is that an environmental consideration, though?
Well, yeah, because if things last longer, they need to be manufactured less often, so you use less energy.
True. But then, is the lifespan of a car determined by the life of its bodywork?
Good point.
It's usually determined by the chassis, or the engine, isn't it?
Is it?
Another one to be researched.
OK, what about post-use then? 2.3.
So, in terms of the main components, the conductor at the center is copper or aluminium, depending on the model. That's then coated with polyethylene insulation and surrounded by steel wire, which provides the armored protection. As the steel obviously needs to be protected from moisture, there's a plastic waterproof membrane around that. Then the whole thing's surrounded by an outer jacket, which, again, is in plastic-based material.
2.4.
That's certainly a scary-looking collection of tools.
Yes, some of them do look quite menacing, don't they?
Is that titanium? The drill handle?
Yes.
I'm an engineer. That's why I,
Oh, I see. Yes, titanium's great. It's expensive, obviously, but very light. That's the big advantage. Ideally, you want it to be lightweight to give you better control. These are the most impressive things, though. The burrs on the end. The latest ones can rotate at over 500,000 revs per minute. They're coated with tungsten carbide, which I think is one of the hardest materials in existence, isn't it? Along with diamond. That's also used. The key requirement is abrasion resistance, of course. Obviously, they need to be very durable. And you don't want them snapping either. The last thing you want is a brittle material. Apparently, that was the trouble they had in the past, making the burr tough enough so it didn't break. I think part of the problem was heat as well. Drilling into a tooth at high speed, you obviously get a lot of heat buildup. You need a good degree of thermal stability. See what I mean? You can actually smell burning. And that's after a few seconds. Imagine the heat buildup after several minutes.
2.5.
Speaking as an engineer, Louisa, my view is that all the materials we use should be genuinely suitable for making watches, and not just chosen as marketing gimmicks. We're often guilty, in my view, of using exotic-sounding materials that are not particularly suitable from a technical standpoint.
Yeah, I know what you mean.
A good example was that debate we had on whether to use submarine-grade steel in some models to give the impression that they're exceptionally resistant to water. Okay, submarine steel's good at withstanding the pressure of being a mile beneath the sea, but it's heavy. If it's not coated, its corrosion resistance is not that good, at least compared with other metals like titanium. It's also fairly poor in terms of looks, in my view. Water resistance isn't a question of metal quality. It's about the quality of the joints and seals you use. So, as a watch material, for me, it's not at all suitable. Tremendously marketable, I'm sure, but...
No, I take your point. But I think it's fair to say that we've never chosen a material for marketing reasons that's insufficiently durable or not adequately built in any way.
Oh, no. No, if anything, it's been the reverse. We've used materials that are over the top, so they can be described with superlatives in advertising.
Ideally, we should be using stuff that's good for watches and good for marketing as well.
Sure, but that's easier said than done. I mean, a lot of the materials that are ideal for the job in terms of scratch resistance, shock resistance, and all the rest of it are either pretty ordinary or their compositions are relatively complex. And they've got complicated names, which means they're not all that good for marketing. That's the problem.
Sure, but the other problem is consumers are not technical experts and they make choices based on their impressions rather than based on facts. That's a hard commercial fact. As hard as submarine steel.
No, I accept that.
So what should our approach be? It's obviously not an easy question.
2.6.
1.
Not particularly suitable.
2.
Exceptionally resistant.
3.
Not at all suitable.
4.
Tremendously marketable.
5.
Relatively complex.
6.
Not all that good.
3.1.
When you look at the various types of plugs and sockets in different countries, most designs have a basic layout that's existed for decades, in terms of the way the pins are laid out and the profile of the pins. And as a manufacturer, the position of our company has always been, basically, to accept that we're stuck with several standard configurations, and to effectively say to customers, we produce all the main formats, take whichever one you want. However, as I'm sure you know, many countries use plugs and sockets of more than one format, and this leads to a comparative situation, with some configurations becoming more popular and others progressively being abandoned. This is particularly true in countries undergoing rapid economic expansion. And because of this process of selection, we're finding that big customers are increasingly asking us which of the standard plug and socket formats in current use we recommend as a manufacturer, which are the best from a technical standpoint. Up until now, we haven't had a standardized company policy to allow us to respond to that question properly. But this project aims to formulate a company policy that allows us to say these are the configurations we recommend, and these are the technical reasons why we recommend them.
3.2. 1.
On this one, there are circular pins for live and neutral. There's no earth pin. This is quite a common format in Europe and Russia. It's also quite widely used in India.
2.
Here, you've got circular slots for live and neutral, and the earth slots got a flat base with one side rounded over to form a semicircle. This type's only used in a few places.
3.
This one has rectangular blades for live, neutral and earth in triangular configuration. This is the standard in the UK and Ireland and a few other places, Malaysia and Singapore for instance.
4.
This plug has got circular pins for live and neutral, and it has a cylindrical slot to receive the earth pin. It's quite common in continental Europe and in parts of Africa.
5.
As you can see, there are circular pins for live, neutral and earth, and the pins are arranged in linear configuration. This is not a very commonly used format.
6.
This is the standard in North America and quite common in Central and South America, used in Japan as well. There are flat blades for live and neutral and a round pin for earth, and they're laid out in triangular configuration, so an extremely widely used format.
3.3.
Rectangle. Rectangular. Triangle. Triangular. Cylinder. Cylindrical. Line. linear.
3.4.
In this configuration, there's a circular slot at the top. It's obviously a blind hole. It doesn't go right through. And that's designed to receive the earth pin, which is mounted on the face of the socket. Then there are two plastic ridges, one on either side of the plug casing, and they slot into corresponding grooves at each side of the socket. In addition, the center of the socket is recessed. So rather than being flush with the front of the socket on the same face, the circular area that receives the plug is set back from the surrounding casing in a recess about 15 millimeters deep. The live and neutral sockets are also equipped with covers just inside the opening. These covers only open when pressure is applied to both by the two pins of the plug simultaneously. So, we need to look at the advantages of this configuration.
3.5.
In this format, the plug slots into the recess in the socket. That allows it to fit in really tightly, compared with other designs. Plus, these ridges and grooves on the sides increase the amount of friction. That helps it to resist pull-out forces even more, so it won't fall out of the socket.
Yeah, but at the end of the day, how securely do you want it to be retained? If it's held in too hard, that makes it difficult to pull out.
That's true.
Plus, it could be dangerous. If you're vacuuming enthusiastically to loud music, let's say, and you pull the cord, you actually want the plug to pull out, don't you? Otherwise, you might rip the cable halfway out of the plug or the appliance.
So, really, we need to compare the pull-out resistance of all the formats.
And determine what the ideal resistance is.
Yeah, okay. What else can we say about this one?
Well, I guess another advantage is, given that the plug's in a recess, if it gets pulled out just a fraction and the pins are still live, nothing can physically touch them.
So you think that's more effective than having insulators round the tops of the pins?
I'd say so, yeah.
This one's also got covers inside the live and neutral slots.
That's a standard feature on more or less every format, though, isn't it?
Yeah, but I think it's something we should look at. I mean, it's obviously a good thing. Anything that stops children from sticking things in is obviously a good idea. The only problem with this system is if the mechanism's too sensitive. It makes it difficult to insert the plug sometimes, and that makes it easy to damage.
When people try to force it.
Exactly. Now, look, if you look here...
3.6.
Most of what we do is sheet metal working. We don't do foundry work, you know, casting and that type of thing. That's obviously a different discipline. But apart from that, we're equipped to do most things to do with metal bashing.
Oh, that's the technical term for it, is it?
I'm not sure what the technical definition of metal bashing would be. A collective term for hammering, grinding, and generally making a lot of noise, probably.
It's actually not that noisy in here, is it?
No, it's not too bad. We had a specialist firm come in a while ago to measure noise levels at each machine, you know, for health and safety regulations. A lot of what we do isn't all that noisy. Things like drilling and milling machines are not too bad, relatively speaking. Anything involving abrasives tends to be noisy, things like grinders, even if they're only hand tools. And that big press over there makes a loud bang when they're shearing steel.
All right.
It certainly saves a lot of time, though, compared with flame cutting or sawing with a grinder blade.
So it's a guillotine?
That's what we use it for mostly, yes.
All right.
3.7. 1.
So, we use high-pressure water jet cutting quite a lot. The good thing about it is you don't need to do any finishing afterwards. The edges are virtually perfect, so they're especially good when you have intricate shapes.
Which would be difficult to finish otherwise.
That's right.
2.
Saw blades are obviously useless when you're cutting curved shapes.
That's right. When you're using any sort of abrasive technique for cutting metal, it inevitably gets hot. And that can alter the properties of the metal around the cut, which can be a problem in some situations.
3.
The other problem with abrasive cutting is it exerts shear forces near the cut. So, sawing is not the best solution if you want to avoid altering the material.
The same applies to guillotining, presumably.
It does, yes.
4.
It's amazing to think that a water jet can cut through steel. You could imagine water cutting timber or soft, relatively soft material, but...
No, it's ideal for metals. Actually, it's not just water that's used. They sometimes add an abrasive powder to the water to increase the cutting power.
Oh, I didn't know that.
The water's obviously concentrated into a very fine jet. Depending on how it's set up, it can take out less than 1/10 of a millimetre sometimes.
Really?
.8.
So basically, our objective is to get key suppliers more actively involved in the design process. So rather than us going to a supplier and saying, we want a specific type of bolt or screw or rivet for connecting these components, can you give us a price? We want to be able to say, we need a way of joining this part to this part. What's the best way of fixing them to each other?
Okay.
So it might be that you say, well, actually, instead of bolting this onto the machine, what about using a weld? Or instead of riveting these, how about bonding them with adhesive or fixing them on with some kind of clip or whatever? Whatever's the most cost-effective solution.
Right. But obviously, we're a supplier of mechanical fixings, so we can only provide a mechanical solution. So if you ask us to design some joints, which is obviously quite an involved job, and then, after all that, a rival firm comes along and says, well, we suggest welding it all together or gluing it together for half the price, it would mean a lot of work for no return. I'm not saying it's a bad idea. It's just that we would have to be careful we covered our costs.
I appreciate that, but the flip side is we want to work with fewer suppliers than we have in the past. So overall, that problem would be offset by the greater volume of work you'd get.
3.9.
So a typical cluster consists of somewhere in the region of 100 balloons. That's using ordinary-sized weather balloons. With about 20 people helping, it takes an hour or so to inflate them all.
An hour or more with 20 people?
Yeah, it's pretty time-consuming.
And is each balloon tied on individually?
That's the way it's often done, yeah.
And is the rope just fastened around the bottom, or...?
Well, some people use plastic cable ties, or you can use tape.
So it's a big job, then, putting everything together.
Yeah.
The harness is suspended from 100 or so ropes, then. Well, how's it fastened?
Well, you can put nylon straps beneath the ropes, so you have several ropes tied to a single strap. Then each strap is fastened to the harness.
I see, so it's like a kind of tree structure.
That's right. And you have different lengths. So the balloons aren't all at the same level. So they fit above and below one another in a round-shaped cluster.
I see. So you inflate the balloons, keep tying them to the harness via the straps, and keep doing that until you take off.
Basically, yeah. The pilots rope to sandbags on the ground. So the balloons are added progressively until there's a marginal amount of lift. Then the anchor ropes are released and up you go, nice and gently.
And how do you control your altitude? You carry ballast, presumably.
Yes, water usually. Those big water bags with taps on, so it's easy to drain out.
And how'd you come back down to Earth?
Well, that's actually a reason for having the balloons tied on individually. You can release them, one by one, which allows you to reduce the amount of lift incrementally.
Oh, I see, because I was thinking surely it would be easier to just have all the balloons contained within a big net to make it faster to assemble, rather than spending ages tying every single balloon on individually. But then if you did that, you wouldn't be able to release them, would you?
No, that's true.
You could burst them somehow, I suppose.
Yeah, I mean, there are obviously various ways of doing it, but I think just...
4.1.
I have a question about the panels on staircase 3.
Mm-hmm.
You know those glass panels around the opening through deck C?
Yes, I know where you mean, yeah.
Well, I've been looking for a cross-section through the deck at the stair opening, but I can't find one anywhere.
Isn't there a note on the general arrangement drawing with a reference to a section on another drawing?
I couldn't find one.
I've got the deck plans out somewhere on here. What's this? Air conditioning schematic. That's no good. Here we are. Deck plan. No, you're right. There's no section mentioned.
I mean, in actual fact, what I need is an elevation showing all the panels from the front. I thought that might be referenced on the main section through the stairs.
There is a full set of drawings for all the internal panelling with details showing exploded views of all the fixing details and sections through the panel joints. Do you have those?
Not as far as I know.
And there's a written specification for the panels as part of the main spec. That might specify the sizes.
Those are obviously what I need then. I want to see how many there are and what size they are. Have those drawings been issued?
4.2.
So, how wide is this panel at the top?
Good question. There's no dimension.
Is this drawing to scale? It's 1 to 5. Have you got a scale rule? Let's measure it. It looks to be about 300 mil.
The golden rule is you shouldn't scale off drawings though, should you?
Well...
It's not so bad if it's actual size on a full-scale drawing, but I'd rather not with this. Let's query it. I'll give them another call in the office.
4.3.
Basically, the client has said they want a super flat finish over the entire floor area. That makes it a free movement floor where vehicles can run anywhere on it. But on the manufacturing process drawings, it shows precisely specified routes for these automated vehicles. So, technically, it should be a defined movement floor where you can just have a few narrow lanes for the vehicles, which are super flat, and then the rest of the slab is just laid to normal tolerances.
Right, so you're questioning the extra cost of doing everything super flat.
That's the main thing, yeah. The other thing is quality. To get the best finish on these super flat floors, it's better to lay narrow widths of slab in fairly long lengths. So ideally, you want lanes rather than big, wide areas.
OK, but maybe they want everywhere to be super flat so they can change the layout of the production line in the future.
Possibly, but even if they want to do that, the surface can always be modified at a later date. It's a thick slab, so there's nothing to stop them grinding a layer off the top. In fact, we could increase the depth of the steel reinforcement slightly when we poured the slab, so there's some extra thickness of concrete over it. So, if they did want to grind a thin layer off a section in future, they wouldn't have problems with shallow cover.
Right, well, let's look into an alternative design for a defined movement floor. 4.4. 1.
I've worked on projects in the past where every single working drawing is circulated to every team, structural, mechanical, and electrical, and it just gets completely out of control. So we want to avoid that situation.
Sure, but after saying that, if someone has to analyze every single revision to determine exactly which team needs it, then that takes a lot of time as well.
Not if there's a proper procedure in place. As long as we make sure there's...
2.
This project strikes me as pretty complex in terms of the amount of integration and overlap between the different design packages.
Yeah.
Particularly between mechanical and electrical teams, so we have to coordinate that. And it's obviously a specialist job. It's beyond my expertise as the overall project manager. So in order to make sure that we...
3.
Thinking about how the separate design groups work together, I don't want to rely too much on scheduled meetings. We don't want questions and problems piling up, waiting to be resolved at a meeting in a week's time or whenever. You all need to be talking to one another on an ongoing basis.
I agree with what you're saying. The trouble is, when you're trying to sort out problems with details on drawings and that kind of thing, you need to meet face to face. And given that we all work in separate offices, it's, we can phone each other, but...
Yeah, you still need meetings.
Especially as there's so much integration between the different packages. The point we were talking about before.
Well, there is a solution to the problem.
4.5.
So, to sum up, as regards design information flow, all preliminary drawings are going to be shown to the senior engineer in charge of each design team. The senior engineers then say whether or not their teams need to receive copies of later revisions. If they don't, they won't receive any further revisions. If they do, they'll be issued with every subsequent revision and later revisions of working drawings. To coordinate the interface between mechanical and electrical design, I'm going to appoint a mechanical and electrical coordinator responsible for liaising between the senior engineers in the teams reporting to me. We're locating all 3 design teams in a single open-plan office, so when anyone's got a question or a problem, they can talk to the appropriate person face-to-face. We still have scheduled meetings to discuss formal issues, but the emphasis will be on ongoing informal dialogue between the teams.
4.6.
There's a discrepancy between these details that you might be able to clarify straight away. On the plan of this plate, it shows 8 bolts. But on section A, here, there are no bolts shown in the middle. So there would only be 6, which obviously contradicts the plan. But as you can see, this plate's going to be bolted to a T profile. So we couldn't put a row of bolts down the middle because they clash with the flange running along the middle of the T. So I propose just going for 2 rows of bolts. The alternative would be to redesign the T-section, which would obviously be a bigger job.
Yes, let's go for 2 rows of bolts, as per the sections.
OK, fine. Will you send an email to confirm that?
5.1.
A race is not just a test of speed, but the ultimate test of reliability. There's an old saying, to finish first, first you must finish. And it's especially true in endurance racing. You're not just competing against rival teams, you're also fighting what you could call engineering enemies, which can cause parts of the car to fail. Things like heat, pressure, vibration, shocks, abrasion. There's continual stress on almost all the components, all the nuts and bolts on the car. The chassis, engine, gearbox and clutch, suspension, brakes, tires, wings, cooling system, they all have to cope with phenomenal levels of wear and tear.
5.2.
Just to give you some examples of the types of technical problems we've had so far at this test. On one of the cars, a nut worked loose on a radiator pipe, which resulted in coolant liquid leaking out. That caused the engine to start overheating. Fortunately, the driver saw the warning light come on, and he switched off before the system had run out of coolant. Then, on the other car, we had a fuel feed problem. The engine cut out on one of the corners. That caused the driver to spin off. We were fortunate he didn't hit anything. But when the car goes off the circuit, the openings in the side pods always clog up with dirt. So those had to be cleaned out. Obviously, you don't want anything blocking the airflow to the radiators. And then, because of the spin, the rubber was flat-spotted. The tires weren't close to wearing out, but they still had to be changed because of the flat spots. And then, while they were putting the wheels back on after that, they had a wheel nut jam. It wouldn't turn. And that's actually how problems tend to happen. Very often, you get a kind of chain of events when you feel that everything's going against you. Having said that, you could also say we were lucky. Fortunately, the radiator problem didn't cause the engine to blow up. And after the spin, luckily he didn't hit the barriers and bend the suspension or snap it completely. And even more fortunately, it didn't crack the tub, the chassis.
5.3. So, what does the warning message say?
When you start the engine, it says, check injection.
Right.
Obviously, it must be some sort of defect in the fuel injection system. The thing is, though, it only happens intermittently. Sometimes you start it and there's no message at all. So it might be a software problem, I don't know. Or maybe it could be a defective sensor.
Is the engine working properly?
It seems to be fine, yeah.
It doesn't appear to be misfiring or down on power?
No, we haven't noticed anything. Presumably it can't be anything too serious. We thought it was possibly water in the fuel system, because it's an outdoor unit. But in that case, I assume there'd be major problems with it.
Has it been refueled recently?
Not that recently.
And was it refueled with diesel stored in your own tank or directly from a delivery tanker?
From a tanker truck.
I doubt it's water then, if the fuel went in directly from a delivery. You said the warning doesn't display systematically.
No.
In what sort of circumstances does it come up?
Well, when you start it up for the first time each day, it comes up. But then if you stop it and start it again a short time after, there's no message. It's when it's been off for a long time that you get the warning.
OK. So it's certainly a question of temperature. It only comes up when it's started from cold?
Yeah, exactly.
It sounds like it's a faulty fuel preheater. It's probably just one of the preheater plugs that's gone. It's only a minor fault.
Oh, right. So it doesn't need urgent attention.
No. It can be replaced at the next service. Keep an eye on it, though. If any other problems start to show up, give us a call and we'll send someone over. 5.4.
Hello?
Hello, Alan. It's Julia. I've just started a landing gear check and found a bit of a problem with some tires. All the pressures on one of the wing blocks are well down.
On the same block?
Yeah, on all the other blocks they're correct. So it seems odd that this one group of tires on one corner of the aircraft are all low. And the strange thing is, they're down by exactly the same amount on every tire on the block.
I see. You're right, that is unusual.
The wear rate's consistent across the whole aircraft, though. There's nothing unusual about the wear pattern.
Are you sure the pressure gauge is working properly?
Well, to be honest, you can tell just by looking at the tires that they're down.
Right. Let me come out and have a look.
5.5.
OK, let's have a look at the coolant first. Oh, the level's OK.
It's full of residue, though, by the look of it.
Yeah, it looks a bit black, doesn't it? Time to change it, I think.
OK. What's the filter like?
It looks reasonable to me.
Is it due to be changed?
It is if we follow the service programme to the letter. The trouble is, if you do that, you end up wasting parts half of the time.
We can take it out and give it a bit of a clean. It'll be all right.
OK. Blades next. They look more or less OK to me. There are no signs of damage.
Yeah. No need to change those. They'll have moved a bit since they were last checked, though. The alignment will need to be looked at.
Sure.
Apart from that, it's not looking too bad.
6.1.
So with regard to the capacity, in terms of the number of people it actually needs to carry, what sort of figure are you looking at?
36 is what we're aiming for.
If you think we can add a few seats without making compromises, then by all means, let's look at it.
I think 36 is going to be at the top end as far as size is concerned.
And as regards the graphics, is the video sequence finalized? Will it be exactly as it is on this DVD?
Unless you have any problems generating the physical effects that go with it, then yeah. As far as we're concerned, that's it.
Right, excellent. We can start looking at that straight away then and get things moving. So regarding the schedules, and what sort of timescale do you have in mind for the whole project?
6.2.
In terms of the physical effects, to what extent do you want the experience to be physical? The degree to which it moves can be varied quite considerably.
Well, I mean, we want it to be physical. That's why we're having a dynamic simulator. But we obviously don't want it to be so extreme that people are closing their eyes and not watching the amazing graphics we've got.
Sure. I mean, it's obviously difficult to quantify something like this in theory, sitting in a meeting room. The only way to determine what's right is to actually sit in a simulator and experience it yourself in practice.
Of course.
So what I'd suggest is, after the meeting, we can strap you into one of our machines and you can assess the possibilities.
Sounds interesting.
6.3.
It obviously has to be lifted with a crane.
Yes, but do the slings necessarily have to pass under the base? Why not come up with a way of hooking onto the side of the statue?
How?
Well, couldn't we drill into it, horizontally, and insert bars into the holes? Then hook onto the bars.
People would see the holes afterwards, though.
We could fill all the holes, couldn't we? Surely they could use some sort of filler that's the same colour as the stone.
They'd never hide the holes completely, though. It would still leave marks, wouldn't it? I don't think that would be acceptable.
Or, alternatively, we could make sure the holes were out of sight. What about drilling into the top, vertically? If the holes were right on the top, they'd be less visible. Then the bars could be set in, with lifting eyes on the end.
The trouble is, if the bars were set in with resin, they'd never come out. They'd have to be cut off, wouldn't they? And this mammoth's lying down, so the top will probably be seen, to an extent.
True.
To be honest, I don't think we can envisage drilling into it. I suppose another option would be to use some sort of grab on the end of the crane jib. You know, like the ones they use for offloading lorries. So the statue would be held by friction. But I can't imagine there being anything capable of lifting 36 tons, especially not something that wide.
No. Have you spoken to the masons about this?
Not yet, no.
Why don't we ask them?
6.4.
So all the steel beams shown on this drawing are going to be fixed to the walls, bolted through the concrete.
Right.
So to bolt through, obviously we need holes in the walls. We can core drill them with a diamond drill, which would obviously be done after the walls have been cast. We drill them ourselves as part of our contract package. Alternatively, the holes can be preformed by putting plastic tubes into the concrete when they cast the walls, in which case the contractor responsible for the concrete structure would do the job.
Okay.
Now, the problem is these bolts won't have much play.
How do you mean?
Well, they've got to fit quite tightly in the holes, so they won't be able to move much. There won't be much space around them to adjust their position.
I see.
So that means the holes have got to be positioned very precisely. If they're slightly out of position on the wall, they won't match up with the holes that have been pre-drilled through the steel beams at our factory.
Sure.
That's the main technical issue in terms of deciding how we form these holes. Obviously, the technical side's not the only consideration. There's also the question of timescales, given that there are a lot of these holes to do, and obviously the question of cost as well.
6.5.
In terms of cost, preforming is obviously a lot cheaper because all you need are plastic tubes, which are cheap to buy and quick to put in. If we do it that way, it'll be dead easy and it'll cost peanuts. Whereas core drilling will be slow, it'll be quite a painstaking job. But
core drilling's more accurate, clearly.
A lot more accurate. I mean, sometimes you can get away with preforming. If you need to get within 20 mil, then it's perfectly feasible. 10 mil it's achievable, but it's stretching it. Anything less than 10 mil, and there's no way you can do it.
And what sort of tolerance are you looking for?
About 10 mil.
So it's borderline then?
It's a tall order. The safe bet would be going for core drilling.
The problem is going to be the schedule, though.
Exactly. I mean, to diamond drill the number of holes we're talking about will take,
It'll take forever and a day, won't it? Whereas if they're preformed, they'd be ready as soon as the walls are cast.
But if half of them are in the wrong place, it'll cost an arm and a leg to put them right. Because if they're wrong, it's not just a question of drilling new ones in the right place. If they're slightly out of position, they have to be filled in first with cement, to avoid having two holes overlapping. So putting them right is easier said than done.
Sure. So, as I see it, the key issue here in terms of feasibility is the tolerance. If the holes can be bigger and there's more play for the bolts, we won't have this problem.
6.6.
So, to be clear about how far we can go with this redesign, we're not aiming to reinvent the wheel in terms of the main components and how they fit together. The reasons for that are, firstly, from a hardware point of view, the existing design has proved to be effective. And secondly, we don't have the resources at this point in time to make fundamental changes to the production process.
So the overall internal layout needs to remain the same?
Yes. We're looking for an evolution rather than designing the whole thing from the ground up. Presumably there is room for improvement?
Well, this model has been revamped once before, of course, but no doubt we can refine it a bit more.
However, given that software redesign isn't an assembly issue and has been the Achilles heel of the existing model, it would make sense to rethink that whole system.
So, for software, back to the drawing board then.
Well, whatever we do, we need to make a quantum leap. Whether that means designing the system from scratch, I don't know. We need to make the whole thing much simpler to use.
7.1. A.
Next week, they're due to start maintenance work on the grain silos in Zone 4. We need to make sure that everyone's aware that all those silos are classed as confined spaces. In other words, no one should go inside them without first doing an air test. And we need to keep a check on dust levels as well.
We've got a CO2 detector here, haven't we? B.
If you walk past that machine while it's running and you're trying to talk to someone, you have to shout to be heard. And as a rule of thumb, that means it should be an ear protection area.
Yeah, but the regs differentiate between brief exposure, when you're walking past something, and continuous exposure, don't they? C. So, is it harmful if it splashes on your skin?
According to the notice, it's an irritant and it's toxic.
But it's not corrosive.
Not as far as I'm aware.
So you don't need gloves and eye protection and masks and all the rest of it? If you get any on your skin, you just wash it off.
I'm not sure about that.
D.
We need to inquire whether or not this maintenance involves welding. There are forklift trucks going through that area carrying flammable liquids. If there are going to be any naked flames or sparks, we'll need to put a proper procedure in place.
Right, I'll get in touch with their people then. 7.2.
So in terms of access, theoretically, there's a risk of someone falling as they climb up a silo or down into one. But there's always an external staircase with a guardrail leading to the top, and there are permanent ladders with protective hoops around them, fixed to the insides, leading down to the bottom. So workers should be able to access these silos fairly safely. The big problem will be getting the welding equipment, the gas bottles, down into the bottom.
Now, they can be lowered down by rope.
Won't they be too heavy?
Not if they use the smaller sized bottles.
We'll need to specify the bottle size in the procedure then.
Yeah, they'll have to take care that the bottles don't fall onto someone as well, that no one's standing in the bottom of the silo while they lower them down.
True. That's another point to mention. Okay, so access isn't really a problem then. The main danger is the fact that it's a confined space, especially given that they're welding with an oxyacetylene torch burning, which will produce a fair amount of CO2.
So they'll need a CO2 detector.
I mean, to be safe, they'll need to test the air before they go down anyway. But we should probably specify that they need to keep the detector with them while they're working and keep it switched on.
Yeah. Another hazard is there'll be metal fumes given off as they're actually welding, which is a different problem to the CO2 issue.
Sure. So really, they'll need a ventilation system down there, some kind of air extractor.
Probably, yeah. And there's the problem of dust as well. They'll have to be very careful about that. If they're welding and there's grain dust in the air, there's going to be an explosion hazard.
Yeah. Would a ventilator clear the dust or make it worse? I suppose if there's a lot lying around, it'd keep blowing it up into the air, wouldn't it?
I'm not sure.
7.3.
Restricted areas are places where a serious danger is present, so it's essential that these should be kept locked at all times. Under no circumstances should anyone be able to access them unless they have a permit to work. In other words, a written form giving permission to work in the restricted area.
And permits to work and the keys to restricted areas can only be issued by the electrical supervisor?
That's right. So that one individual is responsible for electrical safety for the whole plant. Only that person is authorized to issue permits to work.
Presumably, it's important that permits are issued every single time someone enters a restricted area. Each time they do a new job, they need a new permit.
Exactly. They shouldn't be issued for any longer than a full shift.
Okay.
And it's crucial that there's just a single key to each restricted area. The whole idea of having a lockout system is to ensure that only one person has access to switchgear at any given time. So whatever happens, someone cannot switch on a circuit at a switchboard while somebody else is working on it somewhere else in the plant.
If we imagine a technician needs to, let's say they're going to change a motor on one of the lines, they get a permit to work and obtain the key to the switchboard from the electrical supervisor. Then they take the key, unlock the door to the switchboard, switch off the circuit breaker for the motor to isolate it, then lock the door again.
That's right. Then, while they're working, it's vital that they keep the key on them continuously.
7.4.
The main hazard when maneuvering a helicopter close to power lines is the risk of a collision with the line. So before commencing work, it's essential for the crew to have detailed information about weather conditions, especially wind direction and speed. Operating in very windy weather is obviously out of the question. The pilots involved in live line work are highly trained and experienced, and their expertise is arguably the crucial factor in ensuring safety. Another hazard is snagging, as at certain times the platform will momentarily be attached to the power line and to the helicopter, leaving the aircraft tethered. It's essential, therefore, that the cable is equipped with a tension release mechanism, so that if the helicopter pulls away suddenly for any reason, the cable can break free. To prevent electrocution and burns from arcing currents, the crew on the platform wear hot suits. These have stainless steel threads which channel the electricity around the technician's body, allowing the 400,000 volt supply to flow between the power line and the platform. The suits also have a fireproof lining to provide protection from heat, and eye protection is worn as a protection against flashes from electric arcs. Again, training is one of the key factors in ensuring safety. As a precaution against mechanical failure, the suspension cable, platform, and all associated equipment are systematically inspected before each operation to check for damage. And the helicopter is maintained in line with aviation regulations. One additional precaution is taken regarding the helicopter's engines. Only twin-engine craft are used for live line work, so that if an engine fails, the pilot can still land safely.
7.5.
The focus of the course will be on your personal obligations in terms of looking after your own safety and the safety of others. That means we'll be focusing on specific safety regulations. For instance, we'll be looking at personal protective equipment that's compulsory, or activities that are prohibited in certain areas, such as smoking. The majority of the obligations we'll deal with are legal requirements. In other words, they're stipulated by law as part of health and safety legislation. If you contravene these kinds of regulations, it's not the same as turning up for work late or merely breaching your contract of employment in some way. If someone fails to comply with health and safety regs, they're breaking the law. It's as simple as that. I'm sure you're all aware of that, but it is an important point to emphasise.
7.6. 1.
If there's a fire, you shouldn't use water extinguishers on this machine, because it contains electrical circuits and it can cause electrocution. You should only use a carbon dioxide extinguisher.
2.
When you lift this machine, it's essential that you should only use the 2 lifting eyes marked in red. No other parts of the frame are load-bearing, so you mustn't use them as anchor points.
3.
You should take care when you're cleaning below the guillotine blade, because there's a danger that the blade could come down. Before you clean it, you should always set the control lever in the blade-locked position. And you should wear protective gloves while you are cleaning it, because the sump below the blade can contain sharp metal offcuts.
8.1.
We know the client is a very green-orientated company, very big on all things environmental.
Absolutely.
So energy saving obviously needs to be an important consideration in the design. Clearly, it's a big subject and something we need to look into in depth, but one specific aspect of it where I think we can make a real difference is with the building management system, specifically with the way we use presence detectors. And I've had a couple of ideas that I'd appreciate your views on.
Sure.
I think we should put 2 totally different design options to the client. Option 1 is to have a building with maximum automation. So, with the maximum automation option...
8.2.
With the maximum automation option, we put presence detectors all over the place and link them to as many systems as possible. Not just the usual systems that activate the lights when people walk into rooms and turn them off when they leave. We could use presence detectors to control other systems as well, like the blinds on the windows. So, if it's the middle of summer and a presence detector senses that everyone's left a meeting room, a temperature sensor picks up a positive reading from sunlight coming through the glass. The electronics activate the blinds, which automatically come down and black out the room. That would limit heat absorption and reduce the load on the air conditioning, saving energy.
Okay.
Or in winter, if the blinds had been pulled down in the meeting room the evening before, the next morning the sensor detects sunlight and triggers the blinds to raise and let in as much sunlight as possible, contributing to the heating. And there could be temperature measurements to determine which rooms are the warmest, and those sensors set off a circulation system to distribute the warm air through the building. into the corridor or into rooms at the other side of the building or wherever.
So we'd use presence detectors and heat sensors to regulate as many systems as possible?
Yes. Well, that's what we'd have with the maximum automation option.
8.3.
The second option is this. It's a very environmentally conscious company, so I assume that green attitude is shared by all the staff. If that's the case, why is there a need to automate everything in the building when most things can be operated manually? Why doesn't the boss just circulate an email reminding people to switch the lights off when they go out and tell them to lower the blinds when they leave a room in summer so it helps the air conditioning? I mean, you'd save electricity because you wouldn't need to control all the systems automatically, and the money you saved by buying old-fashioned manual controls instead of high-tech electronics could be spent on planting trees or something. I mean, it sounds simple, but...
It's a very interesting idea. We have to bear in mind, of course, that the client's a manufacturer of high-tech electronic gizmos. I'm not sure how they'd feel about this in the long term.
8.4. 1.
The obvious danger here is that you could get a build-up inside the vessel if there's a blockage further along the pipe.
So the vessel needs a safety valve.
Yes, and maybe some sort of warning system as well. It could be something that's triggered by a differential measurement. So if there's a higher reading in the tank and a lower one further along, you'd know there was a blockage somewhere.
2.
We'll need a system for monitoring gas consumption.
What, a meter on the supply pipe?
Well, yes, that would measure cumulative consumption. But we also need to monitor the actual rate of consumption at different points in time during the reaction cycle. And if we have those two parameters, we can then determine the frequency of peaks in consumption, which is the third parameter we need.
So that's a software issue then. As long as the cumulative value is being recorded against the timescale, we can plot the rate of consumption against.
3.
The reaction that takes place is going to be exothermic, but the amount of heat will partly depend on how hot the gas is when it enters the vessel.
Yes, because that input heat can be adjusted.
Exactly. So we'll need a sensor next to the valve to measure the input value as gas comes in, and then another to give us an output value. Then we can work out the optimum input temperature for the gas.
8.5.
One of the biggest headaches in power generation is the fact that electricity consumption fluctuates considerably. So, in order to maintain a continuous supply, we have to make continual checks and adjust the power load we generate. To help us plan those adjustments, we forecast fluctuations in demand so that we can anticipate peaks and troughs. We base these forecasts on a number of different factors. One of them, one of the most important ones, is temperature. During periods of very cold or very hot weather, demand increases. The increase in demand is obviously due to millions of electric radiators coming on when it's cold and air conditioning units working hard when it's hot. Another factor, a key factor, which increases or decreases demand is whether or not it's light or dark in the morning and evening. Obviously, that dictates lighting consumption. So those are the two main seasonal factors. They generally go hand in hand, so on cold, dark winter evenings, the rise in demand is significant compared with warm, light summer evenings. We also take into account what day of the week it is, particularly whether it's a weekday or the weekend. Generally, demand rises during the week, when factories and offices are operational, and then decreases when a lot of them close at the end of the week. So demand falls at the weekend. Those are variations that take place within a given week. During any given day, there are factors such as meal times, when electric ovens are switched on. Obviously, that causes a jump in consumption. Even commercial breaks during popular TV shows can cause blips in demand. There can be a sudden rise when people rush to switch kettles on or heat up snacks in microwaves. and then a sudden fall shortly afterwards.
8.6.
Because electricity consumption fluctuates across a significant range, in order to cope with peak demand, our maximum capacity is equivalent to the top of that band of fluctuation. That means that during off-peak periods, we have significant spare generating capacity. Now, in an ideal world, it would be good to use that spare capacity to generate power and store it for use during peak times. Unfortunately, as you probably know, electrical charge is extremely difficult to store in large amounts. You can't just charge up huge batteries. So we use an innovative technique to store up power potential during off-peak periods.
8.7.
The concept of pumped storage is relatively simple. During off-peak periods, when main power stations have got spare capacity, some of the extra power they produce is used by pumped storage stations to pump water from a low-level reservoir up to a high-level reservoir, where the water's stored. It's then held there until there's a peak in demand at some point the next day. At that point, the water's released, and it flows down the pipes, driving turbines at the bottom, which generate electricity. Obviously, the station can only run for a fairly short period, but it's sufficient to cover the peak in demand. Then, as soon as there's a dip in demand, the water can be pumped back up and held ready for use again. So the effect is to smooth out fluctuations in the output of the main power stations. Some of the main station's spare capacity is used when there would be a trough in the demand curve at night. The peak daytime generating capacity of those main stations can also be lower because the pumped storage stations are there to back them up when there are blips in the demand curve.
8.8.
Questionnaires like this drive me mad. I mean, look at this first question. What percentage of my time do I spend doing technical tasks that use my skills extensively? How are you supposed to put a number against that?
You only need to give a ballpark figure.
I know, but even so, it's difficult to say off the top of my head.
It's easier if you compare it with the second option.
Doing tasks that a less qualified colleague could do. Well, let's say roughly half and half.
Are you sure? Aren't you the least qualified person in this department?
Do you know, I knew you were going to say that. Number 2, technical tasks that add value and tasks that don't add value, such as admin. Add value? What's that supposed to...
Well, do you not do some admin, or do you spend all of your time doing productive things?
Well, no. Nowhere near all of it.
Right, so is it 50-50?
Well, no. I spend more time problem solving than I do on admin, thankfully. Let's say somewhere in the region of 2/3. So about 1/3 on admin. 3. Tasks that are purely technical versus tasks that relate to technical organisation. Well, most of what I do is organisation, isn't it? I spend pretty much all my time on that.
Or in your case, disorganisation.
Nice one. What figure did you put down for added value, by the way? Was it a negative number?
8.9.
At this stage, I'm not asking you to give me a detailed breakdown of all the IT equipment we're going to need. It would just be useful to have a rough idea of what's most urgent.
Sure, well, one of the biggest problems is the screens at the CAD stations. A lot of those need replacing with bigger ones. Roughly speaking, I'd say well over half of them are too small. A good 2/3 of them, actually, so we're talking about 15 to 18 screens, something like that.
Okay. How urgent is that?
Well, I mean, they all work. They all function properly. The trouble is, the engineers spend the vast majority of their time working with these screens. And because the detail on them is so small, it's pretty hard work on the eyes, to the point that it affects productivity, so...
Okay, and what about the big printer in here? I've heard it's a bit of a dinosaur.
Well, it is, but it works perfectly well, and we print next to nothing with it anyway. Most of the drawings are printed at the factory.
Uh-huh.
9.1.
With the aerodynamics, there are 3 development tools available to us. The first is CFD software, Computational Fluid Dynamics. With that, the tests would obviously be virtual, based on a computer model. The second option is to go into a wind tunnel with a scale model or a full-size mock-up. In either case, we'd probably need to use a tunnel with a rolling road.
Would that be necessary?
Well, the thing is, the wheels generate a lot of turbulence when they're spinning, so to simulate that, you need a rolling road.
Yes, I know, but if we go for a bodywork design where the wheels are mostly enclosed, which is likely, would that be an issue?
Possibly not. It depends how fully enclosed they are.
Okay, I'm just raising the question.
Sure, it's something we can look at. The third option, then, is field testing, actually running the prototype outside on a runway or somewhere. So we can use these tools in isolation or as a combination. The question is, how can we gather as much data as possible with the limited budget we have?
Well, we need to bear in mind that the problem with Aero is that it's not just about data gathering. You also have to validate the data. CFD and wind tunnels are not 100% reliable. The acid test only comes when you try out a full-scale prototype in real conditions. We need to make sure that everything is tried and tested outside with a full-scale trial run.
Yeah, but let's not forget we're designing a car that does 100 kilometers an hour. It's not a supersonic aircraft. The aero is not going to be that critical.
Plus, with changeable weather, it's not easy to do back-to-back testing out in the field.
No, of course not. I'm just saying we need to be careful, and we need to take...
9.2.
So, theoretically, the horizontal speed will keep decreasing until the container hits the ground. The higher the drop altitude, the lower the horizontal speed at touchdown.
Sure.
But obviously, the higher the altitude, the higher the vertical speed, up to a certain point.
Absolutely. So, assuming the drop altitude's very low, the vertical speed won't be all that high on impact.
True.
And in terms of protecting the cargo, surely a low vertical speed is the critical factor.
I'm not so sure it's the critical factor. I'd say the horizontal speed's more problematic. Because, presumably, if the ground speed's quite high, there's a danger the container will roll over and bounce along when it touches down. In fact, if you're dropping from low altitude, that's probably inevitable. So if the container rolled and bounced for 50 meters or whatever, then you'd have to have some kind of destructible external envelope to protect it from the multiple impacts, which would be very expensive. So, arguably, rolling is the worst problem, worse than a high vertical impact speed.
You think so?
So, you don't think rolling's a bad thing?
I'm not convinced the container would actually roll.
No?
Not necessarily. The military drop tanks out of flying aircraft at low level, tied to special platforms, and they just slide along the ground.
Oh.
And the systems that eject things out of the backs of planes are incredibly powerful. So, because obviously they fire the container in the opposite direction to the plane, that reduces the ground speed.
Uh-huh.
Plus, they use a parachute that deploys horizontally, which also helps to slow it down.
Of course.
So, based on what they do with tanks, I think we can safely assume that we can stop a container from rolling.
But a tank's got massive weight and a low center of gravity. With a smaller, lighter container, there's no way of knowing how it would behave, not without actually testing it. And even if you tested it 10 times, it would probably behave differently each time. It would be very unpredictable. Whereas if you drop from a higher altitude, okay, the vertical speed is higher, but with a lower ground speed, it would behave more predictably. And that would make it easier to design a cushioning system, because you'd be dealing with a single predictable impact.
Yes, but surely a heavy vertical landing is a huge problem. The force of it would be far greater than...
9.3.
The first time we launched one of these things, we basically just got a plastic washing up liquid bottle, filled it about half full of water, then pumped it up with an ordinary foot pump.
So it was just ordinary household stuff.
Oh yeah, nothing too technical. And actually, there was a bit of a coincidence because the opening in the bottle was just slightly bigger than the fitting at the end of the pump, so there was quite a good seal. So we pumped it up, one of us held the bottle while someone else worked the pump. And we released it, and it went up literally like a rocket. I mean, we expected it would shoot up reasonably fast, but we didn't anticipate just how powerful it would be. It just went whoosh and totally exceeded our expectations. So you can imagine us, a group of 12-year-olds, we were absolutely ecstatic. And having said that, there was one problem. Once all the water had come out, which happened virtually in a split second, the bottle, because it was very light, started tumbling over in the air.
So it wouldn't fly straight.
That's right. But we quickly came up with a solution to that problem.
9.4.
What we did was to get a plastic cup, a strong one, not a disposable cup, and pushed it onto the end of the bottle at the top to form a nose. It didn't go exactly according to plan at first. It stabilized it a bit, but it still wasn't flying straight. So we tried putting water in the beaker to act as ballast, and that worked a treat. With the extra inertia and the fact that it was front heavy, it went like an arrow. So yes, we sorted that problem out. Then the next goal was to increase the power to try and reach a higher altitude.
9.5.
One of the things we did was to experiment with the amount of water inside the bottle. I think initially we expected that the more water we put in, the more powerful it would be. But as it turned out, it was the opposite. What actually happened was, if you overfilled it, there wasn't enough pressure to expel all the water. We reduced the amount of water to about a quarter or a third full, something like that. And we also put some tape around the end of the pump to get a better seal with the bottle. That was really effective. I think we underestimated the pressure we were generating. And certainly we were overestimating the strength of the bottle, because it got to the point where we were firing these rockets up to, I don't know, maybe something like 20 meters high, something like that. So you can imagine the sort of pressure involved. And plastic bottles are hardly up to the job of high-pressure rocketry, obviously. So inevitably, the bottle eventually blew up while I was holding it. I was rolling around on the ground with sore hands while everyone else was rolling about laughing. So I learned the hard way.
9.6.
So how credible is this hoax theory then? I watched a documentary about it a while ago.
Well, some of the questions are quite interesting, but from what I've read, they can all be explained scientifically. You know, like the fact that the stars aren't visible in the sky on the photos. Apparently, it's just due to sunlight on the surface of the moon. It was too bright to see them, that's all.
Isn't the flag supposedly waving in the wind in one of the shots?
That's right, yeah. They say it's because of the pole shaking after it had been stuck in. There's obviously no air, so as a result it kept moving for ages due to the fact that there was no friction to slow it down.
Oh, I see.
Another thing that's been explained is the footprints on the surface. People had said the ground looked wet, so it couldn't have been on the moon. But apparently that's the way that type of dust behaves in a vacuum. It sticks together like mud.
Wasn't there some other theory to do with dust when the module landed? That there should have been more dust or something?
Well, during the landing there was supposedly a lot of dust flying up, caused by the blast from the engines. But when the module's actually seen on the surface, there's no crater visible below it. So the theory is that if it had really landed there, it would have left a crater. But the argument against that is that it had already slowed down substantially by the time it reached the surface, and it was only descending gently because of the low gravity.
Oh. So there was only a bit of surface dust blown up?
That's right.
10.1.
Obviously, a tubular steel tower only gives you sufficient structural strength if you give it adequate protection from corrosion, the big problem with offshore installations. So technically, you could say steel is inappropriate in that environment.
They make ships out of it.
I know, Loretta, but only because there's no cost-effective alternative. But we're not talking about ships. We're talking about fixed structures. The point is, I think we should look more seriously at alternatives to all steel supports. And the obvious alternative is reinforced concrete.
We've already looked into it, though, and it wasn't cost-effective.
Not in the short term, but we didn't really look into it properly over the long term.
But you made the point yourself, Mike, that steel is completely ineffective if it's corroded. And one of the main constituents of reinforced concrete is steel.
It's protected, though, isn't it? It's embedded inside concrete. That's a much more effective protection than paint.
Not necessarily. If we're talking about the long term, as you say, what happens to concrete when it's exposed to the sea for a few years? It erodes, which means the steel eventually gets exposed. You look at concrete coastal defenses. How often do you see the concrete all crumbling away and all the steel exposed?
That's due to inconsistent quality, though. You only get that problem if there's insufficient cover. As long as there's appropriate cover at design level and the construction quality is consistent, then there shouldn't be a problem.
Isn't inadequate cover more of a problem in a slender structure, though? You'd probably have less cover compared with the big lumps of concrete they use for coastal defences.
Not if...
Just a second.
Yes, Hanif?
Let's just think about what we're trying to resolve here. The key issue is, what's the most suitable long-term solution? And in both cases, we're saying steel is necessary, either in an all-steel tubular structure or in the form of reinforcement inside concrete. But obviously exposed steel is unsuitable because of the problem of corrosion. So the question is, what's the most reliable way of protecting steel over the long term? And we have to bear in mind that just because something requires regular maintenance, such as painting, that doesn't necessarily mean it's unreliable. As long as the maintenance is consistent, the key question is, what's the most economical approach? So, painting a steel structure every couple of years is uneconomical only if the cost of painting is more expensive than the additional cost of using concrete at the time of construction.
So, to determine the most efficient solution, we need to assess the lifespan of a reinforced concrete structure. If we know that, we can determine how many times the equivalent steel structure would need to be repainted over that same period, and what the cost of that would be.
Yeah.
But this is really the point I'm making, Hanif. We can't categorically say that reinforced concrete is inefficient unless we look into it in detail.
Of course not. Look, let me make a suggestion. I was thinking...
10.2.
With very tall structures, one of the main loads you need to take into consideration clearly is the mass of the structure, its weight. Due to gravity, that mass exerts a downward load which has to be transmitted to the ground. So that downward force means the structure is in compression, especially near the bottom. Obviously, the closer you are to the bottom, the more compressive force the structure is subjected to. But with tall structures, downward load compressing the structural elements is only part of the problem. Another major force acting on the structure is wind load, which is a horizontal load exerted by air pressure against one side of the structure. Because the structure is fixed at ground level and free at the top, that generates bending forces. And when elements bend, you have opposing forces, compression at one side, tension at the other. And at ground level, the wind effectively tries to slide the structure along the ground, and the foundations below the ground resist that. The result of that is shear force between the substructure and the superstructure. The wind generates tensile loads on the foundations of tall structures as well, as the bending action tries to pull them out of the ground on one side. A bit like a tree being uprooted by the wind. So the foundations need to rely on friction with the ground to resist the pull-out force, just as tree roots do. The action of the wind can also generate torsion. You get a twisting force sometimes when the air pressure is comparatively higher against one corner of a building. Although that's less of a problem with chimneys because of their circular profile. With very large masses of concrete, you also have to think about the forces generated by thermal movement. When concrete absorbs heat from the sun, you get expansion. As soon as the sun goes in, there's contraction. That movement can be significant over a large area, especially as the sun generally heats one side of a structure much more than the other. So there are all kinds of different forces acting on a tall structure.
.3
The record speed exceeded the standard operating speed by a huge margin. It was 80% faster at its peak. So you would imagine that the TGV used for the record run was heavily modified. In fact, that wasn't really the case. The train was modified to a certain extent, but with a few exceptions, it was essentially just an ordinary TGV. As you can see from this slide, one of the biggest differences was that the modified train was significantly shorter in order to make it lighter. There was a 50% reduction in length down to 100 meters, compared with a 200-meter standard length. The coaches being pulled were perfectly standard. The only differences were that some of the seats had been removed to make way for all of the monitoring equipment that was carried on board. And some changes were made to the bodywork to make it slightly more aerodynamic, which meant the drag coefficient was reduced by 15%. The wheels on the modified train were marginally bigger than the standard size. The diameter was increased by 19% in order to reduce the speed of revolution, to limit friction and centrifugal force. And the power of the electric motors was substantially higher than the standard units, boosted by 68%. But none of the changes was fundamental. So my point is, standard high-speed trains can be made to go faster by a considerable amount.
.4
In the late 1940s and early 50s, the United States Air Force carried out a series of experiments to explore how much physical stress the human body could withstand. A key aim was to test how much G-force pilots were able to cope with and see what would happen if they exceeded their limits. Led by Air Force Dr. John Paul Stapp, a number of spectacular tests were carried out at Edwards Air Force Base in California, a location suitable for the experiments thanks to its 600-meter rail track, specially designed for high-speed rocket tests. A rocket sled capable of reaching speeds approaching the sound barrier was mounted on the track. On top of the sled, named Sonic Wind, researchers fixed a seat intended for an abnormally brave volunteer. Refusing to give the dangerous job to a member of his team, the man in the hot seat was John Stapp himself. Over several runs, Stapp was subjected to progressively greater extremes of force. Each time, he resisted. Eventually, the time came to take the ultimate risk, to surpass what many doctors believed to be a deadly level of G-force. And so, on December 10th, 1954, Stapp was strapped onto Sonic Wind for the mother of all rides.
10.5.
That day, Stapp was subjected to extremes of force beyond the imagination. When the sled's rockets fired, he shot from 0 to over 1,000 kilometers per hour in just 3 seconds, subjecting him to 20 Gs. When the sled hit the pool of water in the braking zone, it was like hitting a brick wall. Stapp slowed from the speed of a bullet to a complete stop in little more than a single second. Incredibly, John Stapp survived the ride, although so much blood had rushed into his eyes that he was unable to see for some time afterwards. Before the test, doctors had believed that human beings were incapable of surviving forces greater than 17 Gs. When the sled hit the water, Stapp had pulled a crushing 46 Gs.
10.6.
I think what he's suggesting in terms of acceleration and deceleration forces is reasonable.
Yeah. 2G sounds about right. Anything less than that and the track length's going to exceed the size of the site. And if you start getting close to 3G or beyond that, then that's probably going to be a bit too much for the average passenger.
I'd say so. His calculations for the total distance for acceleration and deceleration seem about right. The problem I have is with the length of the track. I think his 10-kilometre figure is okay for an ideal world scenario, but it doesn't leave much margin for error.
No, because at full speed you're going to be covering, what, a kilometre every 3 seconds? So if there's some kind of problem, you're going to be eating up the kilometres at a pretty frightening rate.
You can say that again. I think he'll need every kilometre of track length he can get on that site, plus some sort of emergency stopping facility at the end of the line, just in case.
Definitely, yeah.
Then I don't know what you think about using wheels instead of skids.
Well, technically, it's feasible to build wheels capable of spinning at that sort of speed, because it's been done on land speed record cars. The only problem is, if you get a wheel failure at the kind of speeds we're talking about, the consequences are going to be unthinkable.
Yeah. I haven't calculated exactly what centrifugal forces they'd have to cope with, but for wheels of about 500 mil diameter at full speed, I worked out they'd be spinning at over 13,000 RPM.
Yeah, that's a lot. Plus, of course, skids should give better frictional resistance under braking.
Possibly.
Maybe not?
Well, the friction from wheel bearings spinning at that sort of speed might be higher, and the skids wouldn't be in permanent contact with the rails, don't forget. But anyway, I think skids are the only safe option.
I'd go for skids, definitely.
And then for the brakes. I think the first point is that for the initial deceleration, even without applying any brakes, the aerodynamic resistance is going to be huge. In fact, that alone might even exceed 2G for a short time.
Possibly. It'd depend how much drag there was, which obviously depends on the bodywork design, doesn't it?
Yeah.
I don't like the idea of a friction system against the rails. It would have to withstand a tremendous amount of heat.
Yeah, I think that's a non-starter at these kinds of speeds. Aerodynamic braking has got to be the best option. Possibly you could deploy flaps initially at top speed, then maybe release a parachute as a second stage. Yeah, maybe deploy the parachute at, I don't know, what sort of speeds do dragsters reach? They use parachutes, don't they? What do they do, 400 Ks?
A bit more, I think. 450, something like that. There's also the option of reverse engine thrust, like they use on aircraft.
In that case, though, you'd still need another system, in case you get an engine failure. But it's a possibility. I think the bottom line is that it needs a combination of systems to make it absolutely fail-safe.